All right,
Recording in progress.
So it's my great pleasure today to welcome today's spoken speaker, doctor, or soon-to-be doctor, Jaryd Ulbricht. So Jaryd started his undergraduate degree at, or got his undergraduate degree at Oregon State University, and then took some time off, and he came and he got his master's degree here, where he basically did a fantastic job. He was such a good grad student, he actually worked with two faculty. He published a paper with me and did his thesis with Dr. Gao, and he spent a summer or two, just one summer, at the Atlas experiment in the LHC, which those are great times, right? Great times before COVID, when we could actually go places in person. But anyway, after that, he got into UC Santa Cruz, where he worked with Stefan Profumo, and he's going to tell us something about that research, which involves baryogenesis, why there's more stuff than anti-stuff. And also he'll talk a little bit about the pathway to go from where you guys are to where he is soon to be. So let's welcome Jaryd. Jaryd?
All right, thank you very much for the introduction. Yeah, so I started here, and I eventually got to UCSC. And so I wanted to give part of this talk as kind of like this is what I did while I was here, and then focus a lot on kind of my current research, but in kind of broad strokes manner. So I won't be going into a lot of detail, but I'll talk a little bit about it. So I'm going to start with this kind of research that I did while I was here, and then move on after that to talk about baryogenesis. So it will highlight as we go through where we're talking. And so we'll start with the introduction. So I moved to Fresno from Portland in 2013. I was really interested in particle physics, trying to learn it on my own, going through papers and stuff, and making absolutely no progress on understanding things. So I decided I really needed to go to grad school. And so looking to what grad school to go to, I saw that at Fresno State they had a new PAC program where I had the opportunity, possibly, to go over to Geneva and work at the Large Hadron Collider, and specifically on the Atlas detector. And that sounded like a lot of fun to me. So I thought that would be really fun. And here is the Atlas detector from above. You can see this big, giant machine they built over there. It's incredibly impressive. And I actually did end up going over there in 2014 to work with the Manchester group and Dr. Alexander O. After I graduated from Fresno in 2015, I got accepted into the Ph.D. program at UC Santa Cruz. I also got married. This is my wife, Megan, who we met here at Fresno State during my second year and her first year. And since then, we have had our son since 2018. Here he is living his best days eating a peach at a farmer's market, and he's really going for it. Also in this time, I have lost probably a dozen pair of sunglasses. So if you've seen them, please let me know. How does this keep happening? How do they disappear so easily? I'm not allowed to have expensive ones anymore. Okay, so let's talk about my research that I did while I was here. So like I said, I went over to the Atlas detector in Geneva, and so a little bit about the Atlas detector and the Large Hadron Collider. It is a 27-kilometer ring of superconducting magnets. And along this ring, they accelerate protons to ridiculously close to the speed of light. And then they intersect at 4 different points along this giant ring where they collide and they shoot out, and we kind of measure and see what comes out. The Higgs was discovered here in 2012 at Atlas and CMS. Atlas is this one over here. For the people on Zoom, Atlas is where the you can see there's the second ring underneath the smaller one. In the center of that is the Atlas detector. So we're probing the standard model of particle physics at the LHC. Here is the standard model on the left. It's comprised of matter particles, which are fermions. Those are the quarks in purple, leptons in green, and we have bosons. The gauge bosons are in red, and the Higgs boson is kind of a yellow-orange here. Now, when the Higgs was discovered, it completed the standard model. But the standard model is not a theory of everything. It doesn't include dark matter or gravity. And so a lot of particle physics is looking for extensions of the standard model. It looks like the screen's getting cut off a little on the side over here, unfortunately. So we're looking for extensions of the standard model in order to form a more complete theory of our universe. So while I was over in Geneva, working with the Manchester group, I was working on a project involving electroweak vector boson scattering, and specifically on anomalous quarter gauge couplings. And you might think that you would get these kind of quarter gauge couplings because if you have new physics above the weak scale, some very massive particles here, at low energies you wouldn't really notice them. Except for the fact that maybe your couplings are a little bit different than you would expect from just a standard, totally renormalizable field theory. So the weak bosons are the W plus minus. The Z, those are the weak bosons. And then you also have the photon, which includes the electroweak, and of course also the Higgs, which interacts with the electroweak bosons. So in your Lagrangian, you might have like a term that looks like this. 4 field strength tensors interacting, so this F thing here is the Maxwell field strength tensor. And normally you would have like 2 of these Fs in Lagrangian, that's normal, but you might think, well maybe I have 4. Right? That's going to be a non-normalizable interaction term, but if you're having an effective field theory, then you might want to include such a thing that comes down from some more grand unified theory or something. So this causes you to have a diagram that has 4 photons that interact. And this you normally don't see. You do have this interaction for the W's and the Z's, but generally this thing, it's going to have a lambda to the 4th down here where there's some very large mass term that suppresses this diagram. And the effect of this is essentially the blue here is the standard model and the red is the, if I add quarter couplings to this, you tend to get a longer tail out here in the momentum space. So your events tend to have a lot higher transverse momentum. So this is a signal you would look for. So this is one of the project I worked on while I was over in Geneva. I mostly used a mathematical package called Find Rules to generate Feynman diagrams. So it's kind of automated. I wrote down the terms into Mathematica and it spit out some complicated file. And then I used a Python package called MadGraph to simulate scattering events and some Fortran code called Pythia, which showers the quarks and stuff into hadrons. I didn't really know much quantum field theory at the time when I was doing this. I kind of knew some particle physics before I went over, but I really had no idea how quantum field theory worked. But I was still able to do some research with a minimal understanding of some particle physics and some basic programming experience. Unfortunately, I could not use this research for my master's thesis because I needed to present it to the Atlas Working Group, and I didn't know what that was. So I presented to the wrong group, came back, and then realized that I had presented to the wrong group and I could not actually use this research for my master's thesis. So I started a second project on excited boson production at the Atlas Detector. So this is an idea that comes about because you're trying to solve the hierarchy problem. A lot of the times, why is the Higgs so light? And a lot of models will introduce new spin 1 doublets close to the weak scale. And these are similar to the standard model weak bosons, the W plus minus and the Z, except they're more massive. And they have this magnetic moment type coupling here. So this kind of funny magnetic moment type coupling gives a really weird signal when you look at it at the LHC, at the Atlas detector. So this is kind of a unique thing you can try to look for. And so we did this. This is a plot that's probably very similar to what you've seen for the Higgs discovery, where you have this kind of line over here. Down here is the dijet mass, invariant mass. So you're looking at what's the invariant mass of 2 really large showers of quarks that come out. And you do some covariant math on there to figure out what that dijet invariant mass is. And if there's a new particle in here, you might see a little bump. It's very hard to see the bump here. But we can kind of see it's just a little bit over the red line, which is the background. And so this is a model where I put in a 2 TeV excited boson. So you can see the bump right there. So again, I did some event generation with a new program called CalCep instead of MadGraph this time, showering and hadronization with Pythia again. I did some detector simulation to send the events into a pretend Atlas detector, so it does some like energy dispersion and stuff to make it look like an actual signal you would get from the Atlas detector. And then we did a sensitivity search, which is basically just looking for that bump in the data. And we found a strong sensitivity for masses that are less than 4 TeV. But I don't know if that was quite right. Again, I had very little knowledge of the underlying theory when I was doing this research. I mostly was working with kind of just my knowledge of particle physics and a little bit of programming. But I did learn a lot while doing this project. And that was really important for me because I feel like you learn a lot better by doing stuff like this a lot of the time, at least for me, than trying to read about it in a textbook. I feel like having just jumped into the research and then having to learn it while I was going, I really learned it a lot better than I may have from trying to just do some research on the side. And so that's, oops. So I thought that was a good lesson for me. Another project I worked on while I was here was with Doug on the time-dependent Aronoff-Kasher effect. And so this is a neutron double slit experiment, essentially. You have neutrons, and you're sending them through a double slit, and you're measuring an interference pattern on the back of the wall. Except that there's a line of charge between the two slits. And this line of charge affects the interference pattern. You have some effect, which is a little bit strange, because a magnetic moment, an object that's electrically neutral, shouldn't feel an electric field. But you do. You can measure a phase shift in the interference pattern. So this is very similar to the Aronoff-Bohm effect, but you basically are switching the magnetic monopoles and the magnetic dipoles and the electric monopoles. So they have, in the top picture here, you have a line of charge, and you have magnetic monopoles going around that line. In the bottom picture of the Aronoff-Bohm effect, you have a solenoid here, which is basically a line of magnetic dipoles, and you have an electric monopole that moves around it. And you get to see this kind of phase shift in the interference pattern. And so we asked the question, what happens when the charge on the wire changes as a function of time? If I have the charge changing, do I see something different in the interference pattern? And our answer was no. As long as the charge changes sufficiently smoothly, there's no weird discontinuous jumps, the phase shift cancels between one path going around this way and the other path that goes around the other way. So that was really interesting, and also in hindsight it seems maybe like that should definitely be the case, because this whole thing is you're introducing a different kind of topology into your space. You're cutting a hole in it where that line of charge is. And as long as the space has the same topology, this is a totally topological effect. So as long as I don't change the topology by suddenly saying there's no charge there, the interference pattern should probably be pretty similar, if not exactly the same, if I'm using the same topology. So this was a very fun project, and it was the first time I had done some theoretical physics, and I really fell in love with theoretical physics at this point. So that's what I decided to keep working on. And I really like theoretical physics because it does weird things. This is the double slit experiment. If you try to look where the electron goes, it stops behaving like a wave. Okay, so now on to what I'm doing now. Now I'm working on some theoretical physics concerning baryogenesis. And so I'll quickly introduce you to baryogenesis and then introduce you to electroweak variogenesis, which is just one special kind of what baryogenesis might be. And then we're going to go beyond the standard model a little bit, see what possibly we can do to generate a matter-antimatter asymmetry. I'll very briefly talk about some new math stuff that I've done. And then that'll be it for baryogenesis. So let's start at the beginning. So the invention of antimatter. In 1928, Paul Dirac introduced his famous equation, which describes the quantum mechanics of the electron. Here's the equation right here. You don't really need to know too much about what that means, except that this psi thing right here is a 4-component object. And these gammas are 4x4 matrices that act on the 4-component object psi. Now Paul Dirac needed these matrices to be 4x4 in order for the math to work correctly. And it was just a requirement to get the anti-commutation properties correct. But what is funny about this is this green part is the electron. And nu is the blue part, which is the positron. And you just got this for free. You needed it to be this way. And so Paul Dirac invented antimatter. And the positron is exactly the same as the electron, except that it has positive charge. It has the same mass, has the same spin. Everything else is identical, except that it has positive charge. And so when Paul Dirac first invented this, and then the positron was observed a couple of years later, not knowing it was a positron at the time, it was just a funny, very light charged particle. But they eventually realized it was the positron. Everyone kind of believed that matter and antimatter existed in equal quantities. There didn't seem to be a good reason to think that there should only be one. And the prevailing knowledge was like, okay, it's matter here, but somewhere else in the universe there's antimatter. And there's a big problem with that because matter and antimatter collide and turn into photons. And so if you look out into the night sky towards an antimatter galaxy, you would expect some free-streaming antimatter to be colliding with the free-streaming matter from our galaxy and colliding somewhere in interstellar space and blowing, I imagine, something like an aurora borealis way out in space. And we don't see that. So it seems like everything's matter. We don't really see much antimatter out in the universe. So why do we see this? Why do we see the hydrogen atom as a proton in the center with an electron cloud instead of this, where you have a negative proton, an antiproton in the center and a positron cloud? The Earth, the Moon, the Sun, these things are all matter. Where the heck is all the extra antimatter? So if you want to end up with the correct amount of baryonic matter today, you need to have had at least one extra quark for every billion quark-antiquark pairs in the early universe. So the asymmetry is actually very small. Most of the quarks and leptons and things in the early universe annihilated and became bosons, became photons. Now it's just kind of a CMB background of photons hanging around. But what's left over is this small asymmetry, where you see mostly matter. So that leaves us kind of with two options. One, the universe began with some small preference for matter over antimatter. It's built into physics somehow. There's just some explicit baryon number violating terms in the full theory of the universe, and that starts us off with some number of baryons larger than we had antibaryons. Or you started out symmetric and somehow generate this asymmetry dynamically. And like I said, well, for reasons that I'll talk about a little bit more, or talk about a little bit more in just a moment, this second option seems to be the one that is heavily favored. The first option, there's a thing called a sphaleron, which I'm going to talk about in a moment. And so even if you start out with some baryon asymmetry, sphalerons will tend to wipe it out anyway. So it'll end up, even if you start out with some asymmetry in matter and antimatter, you'll end up with it being symmetric at some point. And then you have to generate it again. So it seems like starting with it being symmetric and then ending with it with some asymmetry seems to be a better idea. So if there were equal parts matter and antimatter just after the Big Bang, how did we end up here? And that's the question of baryogenesis. And back in the 1960s, this date is wrong, Saccharopsin came up with a criterion for how to generate a baryon asymmetry. You needed three things. Baryon number non-conservation, which seems kind of obvious, right? You have to violate baryon number to get a baryon number asymmetry. You need to have charge and charge parity violation. So in order to have some asymmetry, you have to have interactions behaving differently for charge versus anti-charge. You have to have CP violations, charge parity violation, where charge is just changing all the charges of the particles to their anti-component. And parity means to reflect all the dimensions of space. So there's a more fundamental conservation law in quantum field theory that says that you should always conserve charge, parity, and time, the combination of all those three. So if you are violating CP, you're necessarily violating time symmetry. So basically, violating charge parity means you're violating time parity, which means that if you watch this as a movie and you reversed it, you should be able to tell the difference, which is kind of obvious, because if we start with no baryon asymmetry, we have to end up with some baryon asymmetry. So if you watch that in reverse, you start out with an asymmetry, and you end up with none. And it should be obvious which direction the movie is going. So you have to violate charge parity. And the third thing you need to have is interactions out of thermal equilibrium. And this is kind of a similar reason, but it's more of a statistical finite temperature reason, where if you had everything in thermal equilibrium all the time, processes that violate baryon number in one direction would be just as likely as processes that violate baryon number in the other direction. So in thermal equilibrium, these things balance out, and you wouldn't be able to generate any asymmetry above what you started on. So you need to have out of equilibrium thermodynamics in order to end up with some asymmetry. And what's exciting is the standard model actually satisfies some of these. Did you have a question?
For the to generate baryon asymmetry, you have to have all three of these conditions?
Yes. Yes, this is Saccharop's criteria, which I think was actually in 1966.
1960 something, yeah.
Yeah, it was shortly after 1957 when they realized that the weak interactions actually violated parity. A couple years after that. And so yes, you have to have all of these. And I don't think there's much wiggle room for that. So the standard model satisfies some of these. And so you might wonder, well, can we do this just with a standard model? And this is called Electroweak Variogenesis. So this starts out with the idea of something called false vacuum decay. So a lot of you have probably heard of the Higgs mechanism, where the Higgs gives mass to other particles in the standard model by acquiring a vacuum expectation value, sort of the average value of the Higgs field everywhere in space. So it starts out at very high temperatures, and it has a vacuum expectation value of 0. And as the temperature cools, it acquires some vacuum expectation value. And so you plot the effective potential for the Higgs field. And so at very high temperatures, the effective potential looks like this line here, E. And then as it cools, it gets a little dip in it. And as it cools more, this dip gets just as low as the dip that's at 0. And when you get to B, now this dip's lower. And so now you can tunnel from 0 down to a vacuum expectation value around here at the bottom of the dip of the line B. And so this tunneling process is called false vacuum decay, because in time when the temperature is small enough that you end up with this line B, this is now a false vacuum at 0. It's a higher energy state compared to the energy state that you would find if you were in the vacuum at the bottom of the potential well for the line B. So energetically, you would like to decay down to that point. And this happens via false vacuum decay. So over here on the right, I have plotted what's called the bubble profile. So this is the expectation value of the Higgs field as a function of position in space. So in here at small, this should be an R down here on the x-axis. It's been cut off on the side. This is the radius from the center of the bubble. So down here near the middle of the bubble, you have some, this is shifted, so it's, this is the low temperature Higgs VEV down here in the middle, and then outside the bubble you're out in the false vacuum. So as the temperature decreases, you have this condensation effect of the Higgs field, where the Higgs starts to make little bubbles of vacuum expectation value, and these bubble walls kind of accelerate outwards. So this is kind of, I'll talk a little bit more about this, but this is a first order phase transition diagram. When I have to climb over this little hump right here to get down here, I would release energy. That releasing of latent heat is what makes this a first order phase transition. So if this happens, that first order phase transition tends to heat up the universe around it to release heat. It's like when you try to supercool a fluid. Right? It'll get down really cold, and then you flick it, and it starts to freeze, and the fluid actually heats up as you form the ice crystals. So this happens, and it tends to cause different interaction rates happen inside the bubble at different rates than outside, because these things are no longer, the inside and the outside are no longer in thermal equilibrium when this happens. So the next key ingredient here was the observation that the weak interactions violate parity, actually maximally violate parity. So this was discovered by Wu in 1957. And since they violate parity, the weak interactions conserve charge parity. So if they violate parity, they have to violate charge. So this actually gives you charge violations. So only left-handed fermions actually couple to the weak fields. So only left-handed particles will undergo weak nuclear decay. So left-handed particle, let's start with the right-handed particle, the one on the left. I should have flipped these. That's very counterintuitive. Okay, so the right-handed particle is on the left. Point your thumb in the direction the particle moves and twist your fingers. If your fingers curl in the direction of the rotation of that particle, that's right-handed. You can see the one on the right, which is left-handed. I point my thumb in the direction the particle is moving, and I curl my fingers. I see my fingers curl in the same direction as this rotating line here, so that is a left-handed particle. And it's just been observed, it's just an experimental fact, that the weak fields only interact with left-handed fermions. This is the reason you need the Higgs mechanism, by the way, because if you have a massive particle, I can switch left-handed and right-handed depending on my perspective, my speed relative to the particle. So I can make something look right-handed that used to be left-handed from a different perspective. So how does that work? You have something decaying and then not decaying, depending on how you look at it. That's not okay, so you have to have massless particles in the standard model so that you don't have this contradiction. But then, obviously, things have mass. So you need the Higgs mechanism to make sure you're not contradicting yourself and giving particles mass. And so that's why you put the Higgs in, and the Higgs is charged under weak interactions. It's a doublet field. So left-handed and right-handed fermions are going to interact differently with that bubble wall in false vacuum decay. That bubble wall is going to be a boundary in your space. As the bubble accelerates outwards, you have a different energy density on the inside of the bubble as you do on the outside. And as fermions try to pass through that bubble wall, they're going to reflect or be transmitted. And left-handed and right-handed fermions are going to have different reflection and transmission coefficients, because the Higgs field in here interacts with the weak fields, and those violate parity and only couple to left-handed particles inside. So, and then Electroweak Phalarons, which I'll explain in a moment, convert these left-handed antifermions to baryons. Wait, what's a sphaleron? I've said this a couple times, but I need to explain this a little bit more. So, technically, in the path integral representation of the partition function, this phalaron is an unstable stationary point. So it's a solution of the equations of motion. So it's a classical field. It is the point of maximal energy on a non-contractible loop in configuration space. So that's this diagram down here, the little torus. You make a loop on that torus, and that's essentially the sphaleron, where the surface of this torus is field space, electroweak field space, instead of like a coordinate space. This is called configuration space. And I can make a little loop, and this is the smallest loop I can make down here that wraps around the torus. I can't make that loop smaller without cutting it. And so the number of times I go around this loop gives me something called the Chern-Simons winding number. And the sphaleron energy has these little jumps as I go around the loop once, or I go around the loop twice as I go from one to the next. I can change the Chern-Simons winding number, kind of like the Aronoff Kasher effect I was talking about. This is a topological effect. You've maybe heard the kind of funny anecdote that a donut is topologically equivalent to a coffee mug, and they both have one hole. And so this having a hole in your space totally defines what the topology is. And here, in the weak fields, you kind of have this little hole in here. So you can move around this loop, change the Chern-Simons winding number, and this changing of the Chern-Simons winding number is a change in the baryon number. So this is, you go through and work this out by changing the baryon number, also changes the lepton number, and it's proportional to this change in the Chern-Simons winding number. So that's a little mathy. So maybe a better thing to do is give an analogy. So over here on the left, I have baryon island. And over here on the right, I have lepton island. These are both land masses. Now in the middle, I have a sphaleron. Now that bridge is not land. Baryon is land. Lepton is land. The sphaleron is not land, but you can stand on it. So a sphaleron is a unstable pseudoparticle. It's not really a particle, but it kind of behaves as if it was one. And if I back up to here, an instanton process would go from this vacuum at 0 over to this vacuum at 1. It would tunnel through. A sphaleron is a finite temperature effect, where I have some fields in here and I'm jiggling them because they're hot. And if I jiggle them enough, they can actually hop over the barrier. There's a difference between an instanton and the sphaleron. The instanton tunnels through, it's quantum mechanical. The sphaleron is a thermal process where you actually give it a little bit of, just enough energy for a very short amount of time that it can actually classically hop over that barrier. And doing so changes the Chern-Simons winding number. You go around this loop, and it changes the baryon number. So, in a nutshell, here's the universe. It starts out very hot, and the Higgs has a zero vacuum, or a vacuum expectation value of 0. And then as the temperature cools, around 100 GeV, I start to form these little bubbles, where the Higgs is acquiring a vacuum expectation value. And these bubbles are lower energy density, so they start to grow if the temperature is small enough. And while this is happening, I have left-handed and right-handed fermions are colliding with the bubble wall. The right-handed anti-fermions are kind of passing through the bubble wall a little bit easier, where the left-handed anti-fermions bounce off the bubble wall. They have a little bit of a higher reflection coefficient. So outside the bubble wall, I end up accumulating some left-handed anti-fermions. And this is perfect for the sphaleron because the sphaleron loves to eat these left-handed anti-fermions and turn them into quarks. And so now you start to generate a baryon excess outside the bubble wall. And as the bubble wall expands, these extra baryons, these quarks, drift through the wall of the bubble. And once they're inside the bubble, well, the sphaleron actually tends to turn them back into the fermions. So the difference here is that if this is a first order phase transition, the bubble nucleation is a first order phase transition, then inside the bubble, the sphaleron rate is much smaller. It is exponentially suppressed due to a Boltzmann factor. Out here, the sphaleron rate looks more like a Stefan Boltzmann kind of t to the 4th sort of thing. So it's happening much more rapidly out here in the false vacuum than it is in here. So if you can just generate the baryons just outside the bubble wall, they can drift in and don't necessarily get eaten back up by the sphere. So does electroweak variogenesis satisfy Saccharopsin criteria? No, it doesn't. If it did, we'd have this answer. So indeed, the weak sphaleron violates changes in baryon number and changes in lepton number while conserving the difference between the two. And the weak interactions are only for left-handed particles, so I have some charge violation and some CP violation in the CKM matrix, but it's not enough. You don't have enough CP violation to actually generate a sizable amount of baryons. And even worse, bubbles of the Higgs condensate. As the universe cools, this isn't a first order phase transition. It's called an analytic crossover, so the Higgs boson is actually too massive. You would need the Higgs to be less than roughly about 80 GeV in order to have this first order phase transition. What happens here is you have an analytic crossover, so lots of properties involving the Higgs change as the Higgs acquires a vacuum expectation value, but you don't have a discontinuous first derivative of free energy, and so you don't get this latent heat. And remember, you needed that latent heat so that the inside of the bubble wall and the outside of the bubble wall weren't in thermal equilibrium. If you don't have the first order phase transition, you can't make electroweak variogenesis work. All right, so electroweak variogenesis seemed very promising, but it can't explain the matter-antimatter asymmetry. Well, this is only one possible explanation for baryogenesis. There are many others. And I want to just stress that this is one idea of how to do things. But there's some really nice things about this. One, the sphaleron is a non-perturbative effect. I can't write it as a Taylor series of small couplings. And these non-perturbative effects are exponentially small. And this seems kind of nice because if you built in a baryon number violating process into the standard model, just explicitly write something in that violates baryon number, you would expect to actually kind of get a lot of baryon number asymmetry, but we don't have a lot. We have 1 part in a billion. And so this non-perturbative effect of the sphaleron kind of seems to match pretty well with the fact that we don't have a lot of asymmetry. And said another way, you might worry about fine-tuning the baryon number violations if you explicitly broke baryon number. So maybe you really should be focusing on this non-perturbative kind of thing for baryogenesis. Also, it kind of almost worked, right? If the Higgs was just a little bit less massive, you might be able to do a little bit of baryogenesis with a standard model. So you maybe only need to modify the standard model just a little bit, maybe some modest modifications to actually get this to work. So this stands in contrast to things like quantum gravity and the cosmological constant problem, which probably require a very more fundamental shift in our thinking of physics. This problem, this baryogenesis problem, may be solved with only a little bit of a tweak. And that makes it a unique problem, or a unique outstanding problem in physics today, because we may have a good chance of solving this by changing the particle content to the standard model. For instance, something I've been working on is an extension of the standard model where we add a new scalar field. So you can think of this as a toy model, but you can think of this as like the 2 Higgs doublet model, or maybe a minimally symmetric or a minimally supersymmetric standard model where you add a second Higgs. And the nice thing about this is here's my potential over here on the left, my effective potential. I have 4 minimum now, rather than the 2 minimum I had with just 1 scalar field. So early on, very high temperatures, I'm sitting right here in the middle, right at 0. And as the temperature cools, I'm going to undergo false vacuum decay down into one of these other minimum. And then as it cools even more, I'm going to false vacuum decay down into one of the deeper minimum. And we are today in this deeper minimum, or at least that's the idea, right? You're in the deepest one you have here. And while the Higgs transition may not be first order, maybe the transition that happened before it was. And so you could maybe get some first order phase transitions in the standard model, or extensions of the standard model, by a very simple addition of a new scalar field. And so we've been kind of playing around with this. But in order to actually calculate the false vacuum decay rate, we need to invent a new way to calculate false vacuum decay rates. Or you could put it on a lattice. That's an option, but I don't have access to a supercomputer. Also for the sphaleron, like I said, you need that sphaleron rate in the broken phase to be very small in order to prevent washout with baryon number. So if you generated that baryon number outside the bubble wall and it kind of drifts in, if the sphaleron rate's too large, it's going to get washed out, turned back into leptons. So you need to do that sphaleron rate calculation to make sure your new model doesn't immediately get rid of all the baryons that you wanted. So inside the bubble, the sphaleron is biased towards going backwards compared to what you started with. So outside the bubble wall, you jump to the right. Inside the bubble, you jump back to the left. So there's 2 methods to calculate this, either numerically on the lattice, or you could do some semi-classical computation, which was done in the 90s by Carson, Bach, and Juncker. But back in the 90s, we didn't know the Higgs parameters. And computational limitations, they did like 50-some hours of a super cray computer, and got like 5 parameter points in the whole thing. It took weeks of running this thing to like get 5 parameter points. Today we have much better computers, and so you could really expand on this just by adding in Higgs parameters and doing a little bit more parameter space. But we also want to include some common extensions of the standard model, like adding a new singlet or a 2 Higgs doublet model, maybe some supersymmetry, and see what this does to the sphaleron rate. And large-scale lattice calculations are now becoming more feasible if you do have access to a supercomputer. And so it would be good to have an analytic comparison to these things. I know a lot of people will sometimes see the results that come out of lattice computations and kind of go, I don't know about that. So it would be good to have some analytic benchmarks to compare these lattice computations to. So our goal for the Phalaron rate calculations is to calculate the semi-classical rate, which is this thing up here. So the important part is this exponential, the e to the negative energy over temperature, and this kappa is something called a functional determinant, which I'll explain very briefly a little bit more. Okay, so at finite temperature quantum field theory, the rate per unit time per unit volume is this gamma thing. The E classical is a classical energy associated with either the vacuum bubble or the sphaleron. This is the same thing in both cases. And kappa is this ratio of functional determinants where up top I have a determinant. This U is a function of the classical solution, the sphaleron or the bubble profile that you get. And then here is a Laplacian, so it's a derivative, second order derivative. Now if you had a finite dimensional matrix, I would know what to do with this determinant, but this is a determinant of a derivative operator, so what the heck even is that thing? If I had a finite matrix, well, I know what to do. I take the principal equation here and take the determinant, which means my A matrix could be written as lambdas along the diagonal, and my determinant is just the product of all those diagonal terms. But what do you do when you have like a derivative operator that acts on an infinite dimensional vector space? Well, you could try to do a boundary value problem. You have that operator act on some function psi and let it equal lambda psi, and you figure out what all these lambdas are. And this is what was done by Baca and Juncker back in the 90s, was they went through and calculated a lot of these eigenvalues and then took the product of a couple hundred of them. And then you need to do that again for every parameter point. And so you're numerically solving a lot of these boundary value problems, and if you've ever tried to numerically solve a boundary value problem, it's very hard. It's much, much harder than an initial value problem. It's a very difficult thing to do computationally. And also, this function here, you only know that numerically either, because in the case of the sphaleron or the bubble false vacuum decay rate, this phi is like the bubble profile, which is the equation, the solution of the equations of motion, which is some nonlinear differential equation. So this thing here I only know numerically. And then I'm trying to get this lambda thing numerically beyond the boundary value problem. This is really tough to do. But there's a trick. Don't calculate any of the eigenvalues. You calculate one initial value problem that has this particular initial value, so it's 0 at 0, and the derivative is 1. And then the determinant is just equal to the limit that that function goes to x, or that function goes to infinity, which is somewhat amazing that this actually works. Because I don't need to know any of the eigenvalues, but I know exactly what the product of all of them looks like. And this is way, way easier to do, because this is an initial value problem, and I only have to do it once, and I have the product of all the eigenvalues. This is known as the Yaglom-Gelfand formula. And this particular one is the Yaglom-Gelfand formula. It only works if these are scalar fields and this differential operator is regular at the endpoints. I don't have something with like singular terms, like a Bessel function has a singular term at the origin. You can't do this for like Bessel's differential equation. You can do this for like sines and cosines kind of stuff. So we have generalized this to where you have singular endpoints, and also where this function u is a matrix, and it can include arbitrary many fields. So you can do false vacuum decay with arbitrarily many new Higgs fields in here. And that's something new that we haven't been able to do before, at least in the semi-classical way. You can still do the old version where you calculate the eigenvalues, but you haven't been able to do this trick.
Just so I have it right, so instead of solving for the eigenvalues and then basically like taking the product to get the determinant, you're saying you can solve that equation with 0 there. Yep. So the initial value problem, and then basically you'll find the psi, and then basically the determinant of that thing is then that psi in the limit when x goes to infinity.
Yeah.
And you don't have to calculate any of the eigenvalues.
You don't have to know any of it.
It's slick.
Yeah, it's super slow. Yaglom and Gelfand figured out how to do this. They kind of brute forced a path interval to do it, where they discretized everything and then just showed they had like an infinite dimensional matrix, and they did some limiting procedure, and they showed like, oh yeah, look, it does this. The way I did it was a little bit differently, where I did a lot of spectral theory, and it had to do with some special solutions called the Friedrichs principal solutions of a Stern-Liouville problem. And using those, you can generalize the Yaglom-Gelfand formula to systems of equations that might possibly be singular at the endpoints, as long as the singularity at the endpoints is one of, as long as it doesn't oscillate infinitely often as you go towards that point. You can have something that like blows up like 1 over r, that's fine, as long as you don't oscillate infinitely often, like a sine of 1 over x. So this is. It took like a year to figure that out, but I was very happy when I did. Okay, so still this, I've written this determinant thing here, but this isn't quite right because this thing actually diverges. So I need to take the ratio of determinants rather than just the determinant itself. And so if I take the ratio of the determinants, I might end up with something that might be finite. It's still infinite in quantum field theory. You have to renormalize it, but that renormalization is not too bad, and so you can do that. And you often also need to remove zero modes. Some of these determinants are just going to give you 0 right off the bat because you have broken a lot of symmetries here. The bubble, you've placed it at 0, but it should be placed everywhere, right? There's no reason that the bubble has to nucleate at 0. It has to be free to nucleate wherever you want. So putting that bubble at 0 breaks translation invariance. And so this gives you 0 modes where you have basically you have some 0 lambdas in your product of eigenvalues, and that's just going to force the whole thing to 0. So you need to remove those. Those are not real eigenvalues of your Hamiltonian. So there's a procedure for subtracting those out that we've done and we're currently using. All right, so now on to some conclusions. So I had a little bit of advice or observations for students who are maybe upper level undergraduates or starting out in their master's programs and want to eventually apply to PhD programs. Start working on a research project right now, if you're not already doing it. Start like right now, email somebody tomorrow, try to get in and start doing some research somewhere. You don't need to know everything to start doing research, which I know can be a little bit scary when you want to go up to somebody and say like, hey, I want to work on this research, because you don't want to, it's a little bit embarrassing to feel like you don't know anything. Don't worry about that. You'll learn everything you need to know as you go. Just go ahead and like try now, start working on it, and you may even learn it a little bit better. That's the fun part of the research, is you're learning so much as you go. Also, something that became very useful to me is to learn a programming language. If you haven't already learned a little bit of a programming language, pick one. Here's some good ones. I think maybe Julia might be something that becomes a little bit more popular as time goes on. But these Python, C++, if you're trying to do anything really computationally intensive, Mathematica if you're mostly doing symbolic stuff, and Python if you just want something to work and you don't really care how long it takes to run it. Pick a programming language and get good at it. Just do stuff. It is so useful to be able to do just a little bit of programming. So that's my 3 pieces of advice to people wanting to start to work on research. Conclusions based on baryogenesis. Well, precision calculations of the false vacuum and Phalaron rates could provide key information beyond standard model physics. This might be a new tool to restrict our models to say, okay, this model doesn't work. It doesn't work because it doesn't give us the right number of baryon asymmetry or something. So that obviously excludes the standard model right off the bat. But you might want to use this as a tool to say, for future experimental searches, maybe this is a good place to look for a new particle because this tends to give us the right number of baryons. You also may be able to answer some matter-antimatter questions in the near future. This seems to be a problem that maybe is primed to being solved here very soon. You may not need to do too much to the standard model to actually get this to work. And there's also a new frontier in physics, in gravitational waves. First order phase transitions in the early universe will likely leave an imprint on the stochastic gravitational wave background. So what happens is the bubbles collide. And when these bubbles collide, you break the spherical symmetry of the bubbles. And so this creates stresses in the stress energy tensor in Einstein's gravity. And that sends out waves, gravitational waves. And they tend to be messy, all sorts of frequencies and stuff. And so you get kind of this stochastic gravitational wave background. And you may be able to see it in future detectors. If you build a nice big interferometer out in space and you look out, you may be able to see signs of a first order phase transition. And so it would be really nice if you knew what kinds of models gave you what kind of phase transitions. So when we measure these stochastic gravitational wave background, maybe we can decide what kind of models seem the most realistic. Also, going beyond Feynman diagrams, we've developed some new mathematical tools for non-perturbative quantum mechanics. So perturbative quantum mechanics is like the Feynman diagram stuff. We're expanding in small coupling, sphalerons, and false vacuum decay is a non-perturbative thing. Fundamentally, it's more like a WKB looking evaluation of a path integral. And so this is new stuff. We've done a lot of the, been doing perturbation theory for a long time now. And we haven't been doing non-perturbative calculations in quantum field theory for nearly as long. And I personally feel like they maybe deserve a little bit more attention. So that is it. Thank you so much for having me here today. It was wonderful to come give a talk to all you and see all of you again. It's been too long. I would love to take any questions if you have any, and if you do find any of my sunglasses, please let me know.
Okay, so some advice about sunglasses, just buy the cheap ones.
I do, I still lose them.
Oh, they have long all been thrown out for being too German.
Yeah, that's probably true. Yeah.
At what time did the bubble collisions happen?
Right around a temperature, we would expect a temperature of roughly 100 GeV. So this is the electroweak phase transition. This is for electroweak variogenesis. If you want to change things, then I have no idea. I have no idea when they would be colliding. Whenever the phase transition happens, but that would be model dependent.
Well, before or after the inflationary epoch?
After, I'm fairly certain. I'm not sure.
Okay, because if they were before, they'd be amplified.
Okay. Oh, yeah, I see what you're saying. Yeah. That maybe, I haven't done a lot of gravitational wave physics. This is something that I kind of been reading a little bit about and thinking that this would be really interesting to get into, but I haven't yet done too many of these gravitational wave problems. But I think it is something that's going to be more and more important as time goes on. Thank you very much for that question. I'll certainly look into it.
Yeah, and of course, at such early epochs, it makes no sense at all to talk about redshift.
Yeah.
Because the photons are still so tightly coupled in the hot soup of the Big Bang that
You wouldn't even really be able to see much anyway.
you don't know when they're coming or going.
Yeah. Thank you. Yeah.
Isn't it hypothesized that it's possible for there to be like slightly different gravitational constants in different parts of the universe? So you said that the Higgs boson, like if it had slightly different energy, it would work. Would that be? Do you think that could be?
So you mean like a different Newton's constant
Yeah.
in different regions of space? I wouldn't find that particularly natural personally, but I don't know. So that'd be something like in gravity you would have some kind of spontaneous symmetry breaking that sets the gravitational constant, and then this would bubble like you do with the possible Higgs. But then you would imagine the bubble wall expands at nearly the speed of light very, very quickly. So you would expect to find yourself in the middle of one bubble. And it would probably be very hard to look at different bubbles because you have a cosmological horizon. So these bubbles the walls are expanding about as fast as light can. So you probably would find yourself, maybe there are different regions of spaces which have different Newton's constants, but I wouldn't suspect you'd be able to see them.
Paul Dirac wondered about that. Does big G change over the age of the universe, and that electromagnetic interactions are 10 to the 40th times stronger than gravitational interactions, and that the current epoch is 10 to the 40th times longer ago than this early, than when the two forces decoupled. Is that a coincidence? So Dirac called it the large numbers hypothesis, and it's one of those things that some physicist brings it up every 20 years, a paper or two are published, people think, well, it's an interesting idea, and then it goes back into the drawer, much like magnetic monopoles. A friend of mine at New Mexico State, Chris Churchill, has done astronomical observations of distant galaxies called quasars in an attempt to try and tease out these effects in the spectral lines of quasars, and generated a lot of interest without any firm answers. But oh yeah, look up his papers. His name is Chris Churchill. Yeah. He's at New Mexico State.
Students, do you guys have any questions for Jaryd about PhD programs? Like, I mean, for you guys it might be a bit early, but
Yeah.
How are you funded? You work for a faculty member. You're a grad student working for a faculty member who's got a grant.
I'm mostly TA,
Okay.
primarily.
that's what happens with theorists.
Yeah, there's not a whole lot of outside funding for theory. We had some grants from the Department of Energy, and they explicitly said you cannot use this money to fund your graduate students. It's kind of odd. But so there are GSRs that I get probably for 1 quarter or half a quarter per year, where I just get paid to do research. And really nice thing at UCSC, which I think maybe you guys are doing here now too, with the, if you're a TA, there's a tuition waiver.
We're work in progress. So actually, when you were here, you suffered under that, right?
I didn't have, there wasn't an option when I was here.
Yeah, there was no way. I think it's Gerardo, it's a little bit better now, right?
Well, so the official name is a tuition incentive.
Oh,
I think that tells you the story.
okay.
But how much do our TAs get from that? Like 1,000 a semester?
1,000 pretty much,
Yeah.
yeah. So it's far from paying for your tuition.
Yeah. At UCSC, there's a tuition waiver for a TA or a GSR, so you don't have to pay any tuition. You also have your health care is paid for as well. So you do have to like TA or get a GSR or something to be able to pay for rent, which is insanely high in Santa Cruz. So you do need some income, but at least you don't really have to worry about paying tuition or healthcare costs.
I mean, Jaryd, like, not to cry, but like, when I was an undergrad, I had to take out loans to go through. Most people do. When I went to grad school, I did, right? So did you have to take out loans for grad school, or were you pretty much able to do it without?
When I was here, I did, because I came from Oregon.
Don't tell them the bad side about you. Don't tell them the bad side.
Well, I had to pay out-of-state tuition,
Yeah.
which was a little bit hard to do here. Eventually, after my first year, I applied to the California resident, and so then retroactively they gave me back the out-of-state tuition that I had already paid, which was nice because then I got a lump sum of money that I wasn't expecting. But at UCSC, no loans. No loans at UCSC. I mean, you don't really need them too much if you're not having to pay tuition. Yeah.
Well, just a comment on Jaryd's productivity when he was a student at Fresno State. So I have so far like about 50 students have worked in my group, and Jaryd still holds the record as a student who have given the most artist working group talks.
Wow.
So he has given about 12 talks at artist working group, and all the other students they're not in the same order of talks.
We were doing them like every week about for a while.
Very
And there was also, they were always at like 4 in the morning. So doing it in Geneva, so it was like every Thursday night, and we like getting my slides finished up at like 2, 3 in the morning, and then giving a talk at 4. Yeah, I mean, that was really good to do all those talks. I mean, I got really good at like putting together presentations and also just learning like how to give presentations. And so, yeah, thank you so much for the opportunity to work with you and your group. That I feel like it really helped me. I think being part of the Atlas program here was a big part of what got me accepted into UCSC. I had applied there before, at the same time I applied here, and I did not get accepted my first time. I came here, went and worked with the Atlas program, applied to UCSC again, and then got accepted. That was it. So it was, I think it ended up looking really good on my applications, and I think somebody at UCSC's thought and said like, oh, that'll work. Okay. So if you're maybe interested, that we talk to Dr. Gao if you haven't already. Yeah.
What happens next year?
Next year, I'm applying for postdocs right now. So hopefully next year, I will be working somewhere, doing research. Most of the postdoc positions are like 1, 2, 3 years, sometimes extended to 5, but I'm kind of planning on like a couple years postdoc, and then at that point, hopefully applying for faculty positions or maybe another round of postdocs. We'll see what happens. So ideally, my wife's shaking her head no. She does not want to do another round of postdocs. So I'll try my hardest to get a faculty position somewhere after the first round of postdocs. We're mostly looking in California, so a lot of places around the Bay Area, Santa Barbara, down in LA, San Juan, Berkeley, a lot of those. Mostly looking into programs that are doing I don't know if anybody here has been following the resurgence story over the last decade. I'm really interested in that. Resurgence is this kind of funny thing that happens in maybe in quantum field theories. It definitely happens in classical field theories, where if you do like a perturbation series, small coupling, it's divergent. It's going to be a divergent series. Dyson showed this was true a while back. But then the corrections to that perturbative series are something exponentially small. And so you can possibly calculate the corrections in that exponentially small correction, which are also like a lambda plus lambda squared kind of thing. And what seems to happen magically is the coefficients in the exponentially small stuff are the same as the coefficients in the perturbative stuff. This is required by wanting your observables to be analytic functions of the coupling. And the perturbative thing, you do like some resummation on it, you get like an ambiguity. There's a pole in the Borel plane, and so it's a plus minus sign, but you get that same ambiguity in the exponentially small stuff, and so those two ambiguities cancel if your coefficients are all the same. And so this seems like it might have some kind of, it might be important for renormalization, because when you do the renormalization at small orders, 1 loop, 2 loop stuff in perturbation theory, that's the same renormalization you do in the non-perturbative stuff. It's still order lambda and lambda squared kind of corrections. So if it's the same renormalization, the counter terms you introduce into the Lagrangian have to be identical. In order, you can't introduce new lambda squared terms and still get renormalization to work in perturbation theory. But the connection between the non-perturbative and the perturbative stuff happens between low order and high order. So you have a connection between low order and low order, perturbative and non-perturbative. And then you have a connection between low order and high order, and perturbative and non-perturbative. And so you have this kind of double connection there between these coefficients. Sorry, it's 10 after 4. I should probably stop rambling. But it seems kind of interesting to me, and maybe it has some consequences for renormalization in quantum field theory. Maybe things are not as, you don't have as much freedom as maybe you thought you
so does, actually, that's, I have a follow-up question on that, but actually it's a technical question. So I'll say we're going to go to dinner, so I'll save it for later. But are there any final questions, students especially? No? Okay, well, if not, let's thank Jaryd again for bringing